Hi. In this problem, we're asked to show that a certain statement is true. And in doing so, we'll exercise conditional probability, independence, the law of total probability, and the geometric distribution. And as a quick review, conditional probability is basically shrinking our universe down into a smaller universe and doing probability within only that smaller universe. So what we know is that if A and B are two events, then the conditional probability of A, given that event B has happened, is equal to the probability of the intersection, that A and B both happen, divided by the probability that event B happens. And also, the geometric distribution, you can think of it as the number of coin flips you need until you get your first heads, where P is the probability of getting heads on any given coin flip. And so this is a plot of what the PMF looks like for a generic geometric distribution. You can see that it falls off geometrically as the number of trials increases. Okay, so let's now go back to the problem that we have to deal with. What we're given is that X and Y are two IID, which means independent and identically distributed. So what does that actually mean? It means that X and Y are both have the same distribution and they are independent of one another. And what distribution do they have? Well, they are both geometrically distributed with the same parameter P. So one way to think about that is that you have two friends who are independently flipping coins with the same probability of heads, both equal to P. And X is the number of flips until the first friend gets his first heads, and Y is the number of flips until the second friend gets his first heads. And what are we asked to show? We're asked to show this fact, that the probability of that X equals I for I equals 1, 2, all the way through n minus 1 is given that X plus Y equals n is equal to 1 over n minus 1. Okay, so let's actually try to parse this and see what it's saying. The conditioning part is saying that the sum of X plus Y is equal to n. So going back to our example, what it's saying is that if your two friends in total, they require a total of n flips between the two of them in order to get each person to get their first heads. If that is the case, then the probability that your first friend requires I flips to get his first heads is equal to 1 over n minus 1. And the important thing here to note is that this probability no longer depends on I. So in fact, it turns out that the probability of requiring one flip versus the probability of requiring n minus 1 flips is all the same. It's all 1 over n minus 1. So it's kind of surprising, and at the end we'll come back and actually try to figure out why this is the case. But first, let's try to show that this is true. Okay, so you can see that this fits into the general form of conditional probability. So X equals I, you can think of that as just the event A, and X plus Y equals N is the event B. So let's just apply this definition and see what we get. So in that case, what we get is the probability of X equals I and X plus Y equals N divided by the probability that X plus Y equals N. Okay. Now what we can do is work with each of these two separately. So the numerator, let's deal with that first. What does it mean that X equals I and X plus Y equals N? Well, that's the same as saying that, the first friend took I flips to get heads, and in total they took N flips. Well, what does that imply about the second friend? The second friend must have taken N minus I flips to get heads. And so we can equivalently write the numerator as the probability that X equals I and Y equals N minus I. Because if this is true, then this is true, and if that is true, then this is true. And now, what are we going to do? Well, what we know is that x and y are independent because we're given that as an assumption. And now we apply independence. And because they're independent, this probability involving an intersection, we can just write that now as a product of two different probabilities. So this is just a probability that x equals I times a probability that y equals n minus I. OK, and now we actually know what each of these two are as well, because we know that x and y are both geometric distributions, geometric random variables with parameter p. So what is the probability that x equals I? Well, that's just, we can apply that. We know what the PMF is. So this is just 1 minus p to the power of I minus 1 times p. And what is the probability that y equals n minus I? Well, that means that the second friend needed n minus I flips to get heads. So there were n minus I minus 1 tails, and then heads at the end. OK. So we can simplify this, and this is just 1 minus p to the n minus 2, because we can combine these exponents, times p squared. OK. And now let's deal with the denominator. And to do that, what we'll do is apply or invoke the law of total probability. We'll split this up into lots of different cases. So we're going to essentially do the same thing as this, but for more cases. So the probability that x plus y equals n, we can write that as a sum of lots of different combinations. So for x plus y equal to n, we can think of this as a partition. So first, let's say we want x to be equal to some k. And then we want x plus y to equal n, given that x is equal to k. OK. And what do we sum k from? Well, this is basically the partition. So we know that x is a geometric random variable, so it has to be at least 1. You need at least one flip to get heads. And in order for x plus y to equal n, the most that x can be is n minus 1, because we know that y is also geometric, so y also has to be at least 1. So in order for them to sum to n, x can be at most n minus 1. So that's why we sum this. And this forms our partition and how we applied total probability. All right. And now we can further simplify this. And we know that this probability, the probability that x equals k, is just a geometric, right? So it's just 1 minus p to the k minus 1 times p. And then what do we do here? Well, given that x equals k and x plus y equals n, this is the what we need is that in order for x plus y equal to n, given that x equals k, we need y to equal n minus. We need y to equal n minus k. But now, we know also that y and x are independent, so this conditioning actually doesn't matter. So we can actually just ignore it, and we can just plug in what is the probability of y. Y equaling n minus k. Well, that is just probability that y equals n minus k is just another geometric where we have n minus k being the number of flips needed to get for success. So what we have is 1 minus p to the n minus k minus 1 times p. And we can simplify this and get that this is the sum from k equals 1 to n minus 1 of 1 minus p to the, and if we combine these exponents, we get n minus 2 times p squared. All right, So what we have here, let's highlight the pieces that we want. This is what we calculated for the numerator. And this is what we have calculated for the denominator. So now let's put everything together. And we'll see that the numerator is 1 minus p to the n minus 2 times p squared. And the denominator, well, what we're doing is we're summing this over k. But notice that k doesn't actually appear in the summation anymore. And so every single term within the summation is the same. We just have n minus 1 copies of them. And so what we can really do is just write this as n minus 1 copies of what we're summing over, which is 1 minus p to the n minus 2 times p squared. And now we notice that everything cancels except for the n minus 1. And so what we get is what we wanted as our final answer, that this does in fact equal 1 over n minus 1, which is what we wanted. And the last thing that we should verify is that this actually is true for the range of I that we wanted. And if we think about it, I is, as we went through this, this was the case, that I has to be somewhere between 1 and n minus 1. Okay, so now let's take a step back and think about why it is the case that when you condition on the sum, a geometric somehow became more like a uniform, right? Because in general, the geometric, it falls off as the random variable takes on higher values. So it's less and less likely that you'll need more flips in order to get heads. All right, so without this conditioning on the sum of x and y, the probability of x equaling I should drop off as I increases. But it just so happens that when you add this conditioning, that x plus y equals n, no matter what I is, the probability is still the same. So it looks more like a uniform. So the question is, why is that? And one way to think about it is that because you're conditioning on the sum being equal to n, some fixed number, the universe that you're dealing with has changed. And that is basically what's changing everything. So let's make this a little bit more concrete. Instead of dealing with i's and n's, let's just pick some numbers. Let's say n is 10. Right? So what it's saying is that your two friends combined, they needed 10 flips between the two of them to get their first heads, each one of them. Okay, so now let's say, what is the probability that that the first friend needed only 1 flip? So on the first flip, he got heads. Well, and compare that to the probability that he needed 9 flips. So when I equals 9. Without this conditioning, you know that it's more likely that he'll get heads on the first flip than needing 9 flips to get heads, because that requires 8 tails first, followed by 1 heads. Okay, but so why is it that when you condition on the sum, these two probabilities now become the same? It's as likely that he needed 1 flip versus 9 flips. Well, the reason is that because you know that the sum is equal to 10, then in order for the first friend to need only 1 flip, that means the other friend, the second friend, needed 9 flips. And that is a less likely event. And the combination of these, the first friend needing only 1 is more likely, but the second friend needing 9 is less likely. And the combination of those two, you need both of them to happen, makes it so that it kind of decreases the probability of the first friend needing only 1 flip. And conversely, if you think about the first friend needing 9 flips, that is not a very likely outcome. But paired with that, that also means that the second friend needed only 1 flip, and that is a more likely outcome. And so again, the combination, they somehow cancel each other out so that no matter what, you still get the same probability. And that's kind of the intuition behind why it is that this actually becomes more like a uniform. Okay, so the problem itself was more of like a mechanical exercise where we use the ideas of conditional probability and the geometric distribution along with some algebra. But it's also useful to think more about the bigger picture and see why it is that we're even interested in this statement, why we want to show it. and also think about the intuition behind why it's true. Okay, so we'll see you next time.